Hello there, this is Jude Socrates. Welcome to Multivariable Calculus, where today we are reaching a milestone of sorts. This will be the 30th video in our series. This is for Math 5C at Pasadena City College. So today we're going to look at what's called the fundamental theorem for contour integrals. And I'm sure back in basic calculus, you learned about the fundamental theorem of calculus. So this will be a generalization of that fundamental theorem. Now, what have we been doing? We've been computing contour integrals. Okay, so a couple of videos ago, we found the work done by a vector field, and that is the contour integral of our force F along a curve C. And we saw that it had several steps to it. Okay, first you have to get a parametrization for C, R of t, and then you have to plug in x, y, and z into your vector field, and then you have to take the derivative of R of t. You have to find R prime of t, and then you have to take the dot product of those two vectors, and that's when you get to integrate. Okay, so there are like 3 or 4 steps before you can actually get to the integration. Okay, and then you have to do the integration still to finish it off. Okay, so today what we're going to do is we're going to find an alternative way to do that process, that very long, kind of tedious process, if your vector field is conservative. Okay, so remember that means that it is the gradient of some potential function. So don't worry, we're going to review all of that. But in order to prove the fundamental theorem, we are going to need the multivariable chain rule that we did in that last video. So we will review that first, and then we will get to our main topic. So I will see you on page 234, where we will review the chain rule. All right, so here's what it says. You have a function f in 3 variables, x, y, and z, and let's assume it has continuous partial derivatives. You have a curve in space, which is within the domain of this function, and it's parametrized by R of t. Okay? What we're going to do is we're going to compose R of t with f. All right? So we will plug in x of t into x, y of t into y, z of t into z. So that will be the composition, which we will call h of t. Okay, so if you do that, x, y, and z are gone, and you only have one variable, t. Okay, so if these functions are also differentiable, then your composition h of t is also differentiable. And furthermore, how do you find the derivative? You take the gradient of your function, and then you plug in the parametrization. Okay, so you take the 3 partial derivatives of your function with respect to x, y, and z. And after you do that, you plug in x, y, and z from your parametrization. Okay, and then you take the derivative first of R of t, and then you take the dot product. Okay, so that is h prime of t. Okay, and if you were wondering last time, what is this going to be useful for? Okay, that's what we're going to do today. Okay, so we'll go now next to the fundamental theorem for contour integrals. 2 pages down. Okay, so I was saying earlier, finding a contour integral of a vector field along C has several steps to it. Okay, so each of those homework problems probably took you about 20 or 30 minutes. Okay. So the nice thing about the fundamental theorem for contour integrals is that in a special case, you get to find the contour integral with fewer steps. Okay, there's still work to be done, but it's less effort. Okay, so you have to be given a conservative vector field, capital F. Okay, so that means that we will be able to find a scalar function, little f of x, y, z, so that the gradient of little f is our given vector field. Okay, so if that is the case and we want the contour integral of f along C, in other words, the work performed by f as it moves a particle along C, all you have to do is take your potential function and plug in the 2 endpoints Okay, so the parameterization is begins at A, ends at B. Okay, so this should look familiar to you. Okay, in the fundamental theorem for basic calculus, you have capital F of B minus capital F of A. Okay, unfortunately now our capital F represents our force field. Okay, so you just have to change the notation a little bit. Okay, but instead of just B, we have to plug in R of B. Okay, why is that? Because F is a function of 3 variables, not just one variable. Okay, so you have to get the point in space corresponding to B, the point in space corresponding to A. Okay, in everyday language, you have to find the endpoint and the beginning point, plug them into your potential function, then take the difference. Okay, so another way to write down the fundamental theorem without using capital F is the contour integral of the gradient of F dotted with dr is just F evaluated at the terminal point of the curve minus F evaluated at the initial point of the curve. Okay, so the proof of this is short and sweet and follows directly from the multivariable chain rule. Okay, so what did we say? Okay, we're already set up basically because we have our potential function and we have our parametrization. Okay, so if we create the composition of F with R of t, we get a function h of t only in one variable. This is the same notation that we used in the multivariable chain rule. Okay, and the formula said that the derivative h prime of t is the gradient of this function in 3 variables, where you plug in the original parametrization and you dot it with the derivative of the parametrization. Okay, so we are told that our vector field is a gradient. Okay, so we replace capital F with the gradient of little f and dotted with dr. Okay, but wait a minute. It's almost like it's rigged. Remember, what is the meaning of dr? It's r prime of t dt. Okay, so we have the gradient of f. You plug in the parametrization, x of t, y of t, z of t. Oh, wait a minute. That is the gradient of f evaluated at r of t. Okay, so this thing is just the gradient of f evaluated at r of t. And then we compose with r prime of t dt. Okay. But now, oh, look, it looks like I actually duplicated that. I'll be able to delete that when I do my edits. So this is basically just the derivative h prime of t. Okay, so now we're back to basic calculus, one variable calculus. Okay, so we know that an antiderivative for h prime of t is just h of t. Okay, so we plug in b and a, and we get h of b minus h of a. Oh, but wait a minute. If you have t is b, then you have f of r of b. So that's what we have over here. And when t is a, you just get f of r of a. Okay, so that is the proof of the fundamental theorem for contour integrals. Let's go to our workroom, and I made a fresh example just for you. Okay, here's our example. It's pretty substantial. It's kind of scary looking. We have a vector function. I'm not even going to say all of that and all of that and all of that out loud. Yeah, I had to spread it over 3 lines, okay? So we will assume that this ugly looking field is conservative. So we will look for a potential function, little f, for this ugly vector field. Okay, so we want the gradient of f to be this function. Okay, but of course, what we really want to do is to apply the fundamental theorem for contour integrals to find the work done by this force as it moves along a curve C, where C is just a line segment from this initial point to this final point. Okay. So there's no such thing as a free lunch. What we need to do is find a potential function for this ugly vector function. Okay, so in other words, this first component should be the partial derivative of f with respect to x. Okay, the second should be fy, the third should be fc. Okay, so let me write that over here. We want to look for this single function, only one function, little f, so that partial of f with respect to x is this monstrous thing. Okay, so let me emphasize, we want a single fxyz, so that the partial of f with respect to x is this, the partial of f with respect to y is this, I don't even, you notice there was a little typo, there was an extra 3 over there. I think it came from that 3. Hopefully I caught it in time. So we want the third partial with respect to z to be this third component. And I checked that that plus 3 there is important. It is part of that component. Okay, so check it out. We got 4 terms here, 4 terms here, 5 terms here. Okay, so this is how I like to do it. To find f, we basically need to do a sequence of partial antiderivatives. Okay, these are the desired partial derivatives. So to find the original function, we need to perform antiderivatives. Okay, so we're going to do this basically in 3 steps, one for each partial derivative. Okay, we're going to have 2 preliminary answers before we get to a final answer. Okay, so the strategy will be, let's work on the term with the most, the component rather, with the most number of terms, 5 terms. So we get the biggest possible f that we can get just from the first step. Okay, it's going to grow, it's going to change as we work on this. Okay, so let's write that as the antiderivative of this would, oops, sorry about that, the antiderivative of this, let's see if that'll work now. Okay, there you go. With respect to z must be our f. Okay, plus something. Okay, so I will kind of leave that in suspense for now because, well, back in basic calculus, we do a plus c, right? The antiderivative of something is a function plus c. Okay, so yeah, I will maybe leave it a little bit mysterious for now. Okay, so we are going to take an antiderivative with respect to z. So what's going to happen? Okay, so this term, we are going to get an extra z. Okay, how about here? We have z squared over 2. So we want minus 4 x squared y z squared. Okay, there's a z here, so we want z cubed over 3, so that will turn into 5. Plus 5, cheat a little bit, xz cubed. Okay, the derivative is 15xz squared. Yeah, how about this one? There's no z there, no z there, so we are going to get extra z's for both of those terms. Okay, so that is our first preliminary answer for little f of xyz. So I'm going to put that over here. So this function that we want is this plus some constants. Okay, so the constant actually goes with our preliminary answer. Okay, so yeah, I'm going to erase that. So what does that mean? Okay, usually in basic calculus, we just put a plus c there because when you take the derivative of a constant, it becomes 0. But wait a minute, we have a partial antiderivative here with respect to z. Okay, so this means that when you take the derivative of this thing with respect to z, you will get this where it came from. But what will happen over here, we're only taking the partial derivative with respect to z. Okay, so if we have something here that only contains x and y, it will also disappear. Okay, so the correct notation would be c of x, y. Okay, so this means you have a function, capital C, which is not constant. It is constant in z, though, meaning it only depends on x and y. Okay, so we are now going to have to find who is this c of xy. Okay, so to complete the answer, we need to find c of xy. Okay, but of course, we only worked on one component, the z component. We still have two to go. Okay, we need to match the partial derivative of this preliminary answer with the first component and with the second component, respectively, rather. Also respectively. Okay, so, but we want fx. Okay, so we want the partial derivative here to be equal to this component. Okay, so what have we got? Let's copy this over here. Okay, what is the partial with respect to x of our preliminary answer? Okay, I see an x cubed there, so drop the 3, you're going to get 21 x squared, y squared z. I see an x there, so I have a minus 8. Drop the 2, decrease by 1, so it's minus 8 xyz squared. I see an x here, power 1, so that just goes away. Oh, check it out. There is no x here, so that goes away. And there's no x there, so that goes away. And what about c? We need to take a partial derivative of that c as well. Okay, so far, so good, because that first term is this first term. Okay, so they match, thank goodness. This second term is that second term. So far, so good. 5z cubed right there. What's missing? Duh, this one. That one's missing. Okay, so to match perfectly, let me put some more space here. To match perfectly, we need this partial derivative, c sub x, xy, to be the missing term, which is, it was this one. Yeah. Okay, so that means we have to do another partial antiderivative. Okay, so the function that we want, c of xy, must be the partial antiderivative of this function with respect to x. Okay, so that is partial antiderivative of minus 18 x squared with respect to x. And we can do that. X cubed over 3, cancel the 3, we get minus 6, right? Minus 6 x cubed, okay? Plus constant. Okay, so let's call it d this time. Okay, so let's see if you're following along. Okay, this is a partial antiderivative with respect to x only. Okay, so that means if you take the partial derivative of this answer with respect to x, you should get minus 18x, which we do. Okay, but d doesn't have to be just a constant, right? Because we're taking a derivative, partial derivative with respect to x. if D contains a Y, that also will disappear. Okay, so D can depend on Y. Okay, can it depend on Z? No, because C can only depend on X and Y. We have already taken Z into account when we did our first step with the integral with respect to Z. Okay, so now we are just missing our D of Y, and we get to update our function. So we will update, let me put a colon there. So we are missing the minus 6x cubed, because that's our c of xy. So change c of xy, replace it with this. Okay, so to complete the answer, we need to find now d of y. Okay, so yeah, I'll copy that. To complete the answer, we need to find d of y. Okay, so you see what's happening. We had a preliminary answer, level 1. We integrated with respect to z. Okay, we were missing a function in two variables, x and y, so we did a second antiderivative. Okay, so that's over here. But to find the c of xy, we needed to match the partial derivative with respect to x in the first component, okay, which we find in the first component of capital X. Okay, and we notice, oh, everything's there except the minus 18x squared. Aha! So we take that antiderivative, we get minus 6x cubed. We're now missing a constant function with respect to y. Constant in x and z, there is no x or z in d, only y. Okay, so to complete the process, we need to match the final partial derivative, fy. Okay, so we want, okay, fy to be this. Okay, so what do we have so far? This is our current candidate. Okay, who is your partial with respect to y? Okay, so I see a y squared, drop the 2, 14, and so far so good. I see a y there, power 1, so goodbye. I don't see a y there, so that entire term goes away, goodbye. But I see a y to the 4th there, so drop the power 8, y cubed z, thank goodness, because that's over there. What are we doing? Partial y, right? 3z, thank you for playing, goodbye. No z there either, thank you for playing, goodbye. And, so we need the derivative d prime of y. I did not put d sub y because that is an actual one variable derivative, plain derivative. Okay, is everybody there? Anybody missing? Yep, this term is missing. Okay, so to match perfectly, we need, it's one thing about not writing on a whiteboard. Oh, please. You don't want to see my handwriting. We want d prime of y to be equal to 18y. Okay, so there you go. So, who is our d of y? D of y is the antiderivative and antiderivative for 18y dy. Okay, so of course over 2, so that gives us 9y squared. Plus, what's the next letter? Maybe an E, or if you like, capital K, K for constant. Okay, there you go. And we're out of variables. Okay, we have used all 3 components. K can be any real number. It has to be now a constant no variables involved. Okay, so we have our final potential function. Spelling, update. We have this plus d of y. Okay, so our d of y is this. Okay, so that is we have reached our potential. You know what? Let's check, because we have Maple to help us. This is our given function. Let's copy that over here. And let's see if we have the right answer. Okay, so copy that here, and we go. Compute vector calculus gradient. Is it all there? We scoot out of the way. 21x. Yes, 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 yes. Yes, yeah. Okay, there you go. Yeah, it's all there. Yeah, I think that 3 came from down there, that errand 3. Okay, great. Okay, so I hope you agree that this process is kind of fun. You know, you're trying to look for this function. You're doing antiderivatives, partial derivatives. It's a lot better than the horrific algebra that you would have to do by parametrizing this line segment. Okay, so you need minus 3 plus 3t minus 2t. 1. Okay, at least that's a constant. There's no t. But then you're going to have to plug in all those 3 horrific functions into that potential. Into these 3 components. Okay, and then take the dot product with the direction vector. Yeah, there's so much algebra and arithmetic involved with that, and that's not really calculus, right? There's not much thinking involved there. There was quite a bit of thinking involved looking for this potential function, don't you think? Okay, so now we get to use this potential function to find the work done by F moving a particle from point A to point B. Okay, so it looks like the z-coordinate did not change. That's fine. So the idea is to plug into our potential function the 2 endpoints. Okay, so plug in x equals 0, y equals -2, and z equals 1 into our potential little f. Okay, and of course I picked 0 so that those terms will go away. Same thing with 1, they essentially go away. X, oh, okay, got some here. So we have these 2 terms, and then x goes away plus y squared. Okay, so those are the only terms that survive, thanks to the 0 in our x. Okay, and z is 1, so goodbye and goodbye. And so with y equals -2, -2 to the 4th power 16 times 2 is 32, plus 3, y squared 4 times 9 is 36. Okay, so 32 and 36 is 68, plus 3 gives us 71. Excellent. Okay, so next we take the initial point. Okay, so now we plug in x equals -3, y equals 0, and z is still 1 into f. Okay, so get back here and get it here. Okay, so this time y is 0. So goodbye, goodbye. Where else is y 0? Goodbye and goodbye. There you go. Those are all gone, gone. And z is 1, so that's gone, and that's gone. Okay, this is the kind of arithmetic that's fun, right? So now x is -3, so multiply by -3. Negative 3 cubed, so negative 27. Yeah, we should probably use a calculator on that, or on the whole thing. So we get 150. Okay, so the final answer is you take this. What do we want? We plug in the terminal point. We did that over here. So we get 71, and then we subtract the value at the initial point. Okay, there we go. So the final answer is negative 79. Now, unfortunately, there's no way for us to check this answer except by doing it the old way, which you definitely don't want to do. Okay, so we'll just believe that we did everything correctly. Okay, so there's one more thing I want to do before we end this video, and that is go back to gravitation. All right, so the gravitational field is one of the best examples for a conservative field because it's almost obvious what the potential field is, okay, but we gave it to you anyway. So now we can use the method that we tried in the earlier example to see, can we come up with this potential function in about the same way, okay? So in other words, we're looking for a function whose partial derivatives match these three components, okay? But of course, we're going to need to bring this into our vector because there are variables in here, okay? So we need the partial of f with respect to x will be gm over this multiplied by negative x, okay? So we will take an antiderivative for this with respect to x, okay? So we'll need a substitution for that, okay? So luckily, there's an x here, and that's exactly what we need, because if this is our u, simple u substitution, partial with respect to x is just 2x. So we get our 2x dx. So we already have an x dx over here, okay? So if that is our u, du is 2x dx. So we have gm, constant, take it out. We have u to the 3 halves in the denominator. And then minus x dx, we need a minus 1/2 du. Okay, so we can take the 2 out, of course. And we have, and the minus 1/2, I guess. So we have du over u to the 3 halves, that is u to the negative 3 halves. All right, power rule, negative 3 halves plus 1, you get negative 1/2. Okay, so we get u to the negative half over negative 1/2, and then something wonderful happens. The 2's cancel, the minuses cancel, so we just get u to the minus 1/2 and the 2 constants. Okay, so we bring back the u, put it in the denominator because it has a negative exponent, that's where it belongs. And we said before, not so fast, that's only a partial answer, no pun intended, because we still have a function here that must contain only y and z, okay? And the partial derivatives of this whole thing, actually, should match the 2 other components, which we see over here. So, not so fast, we're not quite done yet, even though, oh, wait a minute, even though, isn't that already the answer that was given to us right there? Yes, it is, okay? But now we get to verify that that is the full answer. So if you take the partial derivative of this with respect to y, what's going to happen? Well, we have 1 over something to the 1/2, so to the minus 1/2, so you get minus 1/2, this to the minus 3 halves, and then chain rule, you get a 2y, ooh, 2y, so the 2's cancel, and you do get the minus y that we want over here. Same thing with the minus z. Okay, so yes, we can check that those can be, partial derivatives will be just 0. They will go away. So that is just a pure constant. And of course, the simplest choice for that constant would be 0. Okay, so you might notice that we really are concentrating on something that look like definite integrals, okay, plugging in endpoints. Okay, we want a final numeric answer. We don't want any of this plus k business. Okay, so now that we know that, we can find the work done by the gravitational force if you know the endpoints of a path. Okay, so we're going from point A to point B, and we can use any path that we want as long as you don't go through the origin. Okay, why is that? Because you definitely don't want to go to the center of a planet. Okay, you will be crushed by gravity, if not all the rocks around you. Okay, so our vector field is definitely defined everywhere except the origin. Okay, so what do? We plug in our endpoints. So we're basically, we're just squaring. That sounds familiar, right? We're basically looking for the distance from this point to the origin. Okay, so 9, 25, 36, that adds up to 45 and 25, 70. So we have gm over square root of 70. Repeat for the initial endpoint. We get 4 plus 1 plus 16, 21. Yay, we get square root of 21. So the work done is just the difference. Okay, we have f of b minus f of a. We can factor out the constants gm, and we get this as our final answer. And is that positive or negative? You'll get square root of 21 here, minus square root of 70. Square root of 70 is bigger. It's a negative work. Ooh. So why is that? Well, we're going from a point closer to the origin than the initial, the final, the terminal point. Okay, so because gravity is attractive, they're basically pulling the object away from the planet. Okay, so gravity is doing negative work. Guess who's doing all the work? You are. Okay, because it takes energy to pull it away from the gravitational field of that planet. Okay, so that is our video for today. I hope that you enjoy it. Good luck looking for your potential fields. May you find your potential. And I will see you in our next video when we begin our journey on our final kind of integral, which will be surface integrals. Although there are actually two kinds of surface integrals that we're going to look at, in the same way that we had a contour integral for a scalar function and a contour integral for a vector field. We will also do surface integrals for those two kinds of functions. So until our next video, I hope you enjoy the rest of your day. Bye-bye.